So with this, we can start with the first presentation of this webinar. For that, I would like to invite Dr. Naveed Anwar. He will give an overview of ACI Design Principles. So over to you, sir.
Thank you so much, Ahmad, and welcome everyone. This is actually, you might know that this is a second part of the series that we are doing webinars on nonlinear analysis, performance-based design, and also the code-based design linked together. And so this part, most of the audience, I think, are the same who attended the previous one. And my presentation also, some part is derived from the previous discussion because it's quite linked to that. All right, so we start this one again. This time we are looking at ACI 318. As you know, this is the primary code for concrete design in many countries, and many countries' codes are based on this one. Obviously, there are provisions in Indian code and some other national codes which are different, but the philosophy of the design still remains the same. So although we are focusing on ACI, I think a lot of the principles are going to be common for most of the design codes because we are going to talk about nonlinearity and nonlinear modeling, which are general principles. So last time when I presented, I asked this question, is my structure safe? And this question is so relevant today because just yesterday, as you might know from the news, we had this major earthquake in this region, starting from Myanmar, affecting Bangladesh, India, Bhutan, Laos, and Thailand significantly. Especially Bangkok, because Bangkok is based on a soft basin. So these seismic effects are amplified significantly by a large number. So the buildings, and especially tall buildings in Bangkok, suffered significant oscillation. And I will talk about that a little bit. And yesterday, when I was going home, I was on the highway when the earthquake happened. And this is what I noticed at that time. And you can see the poles swinging. And I didn't know what happened, whether my car was just moving sideways. And I thought I had a flat tire, but actually it was an earthquake. And then I look at the cranes, they were moving also very badly. And at that time, one thought keeps coming to my mind, is this bridge safe? I was thinking whether this bridge will sustain because it was shaking so badly. So the question, is my structure safe, became so relevant and so important at that point in everybody's mind. Second one, you will see this is a shaking on the elevated train station in Bangkok. And you can see how violent this shaking is and how scary it must be for the occupants and the people around it. And the third one, I'm sure you have seen this video also, is actually a video of a building under construction. I pass through this building often, and you will see that, first of all, it just started to collapse just like that and completely collapsed. And people were working there were people under that. And unfortunately, a lot of people lost their life. And you can see the catastrophic nature of the collapse due to this building. So we can see a few, firsthand information about the significance of earthquakes and the impact on the structures just from yesterday. So that sort of puts the context to our discussion today. This is the picture from that collapsed building that I showed you in Bangkok. This is, on my way, I look at it every day under construction, but unfortunately, this happened. And this is, as you can see, it's a flat slab structure with core walls, which is, might have been one of the reasons. We don't know yet, but of course, a lot of investigation will be done. But this is just a collapse. A lot of buildings suffered significant non-structural as well as structural damage. The building that I live in, we live in a 37th floor. It was shaking so violently that my family had to run down the stairs, 37 floors. It was so, such a scary moment for them. So we can see that earthquake shaking and the building response is extremely important. The whole city was shut down after that. So this is a disaster which we are trying to prevent as a structural engineer, as I mentioned yesterday. So basically, we are talking about the vulnerability of the built environment, which in this case are the buildings and infrastructure. Some bridges also got damaged. So we are looking at reducing this vulnerability. And if you reduce the vulnerability, then we hope that there won't be a disaster. So for this one, the design codes play a significant role because they provide us the guidelines and the rules and the procedures so that we can do this risk reduction for the public. And we talked about this last time quite a bit. So now the building codes ensure this one through requirements, acceptable solutions, prescribed and detailed procedures, rules, and limits, mostly based on experience and some rationality. And the spirit of the code is to provide public safety, and that's what they intend to do. And the intention is, and last time we had a question about that also, that the compliance to the letter of the code will result in the safe structure, which means the spirit of the code. But there is no way to verify this, that this will happen. But this is what we are discussing today, how to verify that after you have followed the code, will it work or not? And that's exactly what this webinar is all about. So if you see how codes look at safety, that you look at many things, appropriate, estimate of the hazards, defining the procedure for analysis and design, providing specifications for construction and monitoring, safe rules for detailing especially, and limits on structural member strength and so on. So all these is covered in the codes. But the basic perspective is capacity should be more than demand, whether it's a brittle capacity, the strength-based capacity, or ductility-based capacity. Both should be more than the demand. So we had this formula yesterday. The reduced capacity should be greater than magnified moments with some factor of safety. So we talked about DC ratio, and we talked about safe and unsafe portions of the DC ratio. But it is quite clear that DC ratio is much more than that, because according to the code, the acceptable region, let's say for a column, is here, while the computed theoretical capacity is the green line, and blue line is the actual expected capacity, which will happen due to increased strength beyond what we designed for. We provide more material and so on. I will talk about that in a minute. So that's the principle on which the safety or the DC ratio is based. This is how we design it. But then the question is, will it be sufficient when the time comes, when it is tested for earthquake? Because this procedure is not suitable for earthquake. So seismic effects, we are looking at now ASC and ACI approaches, and they are actually combined together. So ASC 3189, this code here is what we are discussing here. And then we will go into the more details of this code. Now, before we do that, we have to look at ASC 716, on which the ACI code is based, because the demand is coming from the code, from ASC, and the capacity is more or less coming from ACI. So the two have to match. So the design level typically for non-earthquake forces, for example, wind or gravity, is elevated up by factors, load factors, to bring them to the design level, and the capacity is reduced by the capacity reduction factor. But earthquake is opposite. The design level earthquake or the actual earthquake expected is very, very large, and we cannot design it at that force level. So it is reduced to a design basis earthquake, which is 2/3 of that, and which is further reduced to a design level earthquake, which is divided by a factor of R, or response reduction factor in other codes. So basically, we bring the earthquake down, unlike the wind or gravity, which we take them up. So then the factor of safety that we have incorporated are just never going to be enough to reach that level that we started with first place. So we can't reach the expected force levels. So this is done through a nonlinear response. We expect the structures to go nonlinear during that stage, reduce the demand because of the period lengthening, energy absorption, dissipation, as well as because of the ductility. But the problem is this nonlinear response is higher than the design level for several reasons. The first one being the capacity reduction factors. The second one being that the actual material strengths are typically larger than we specify steel strength, concrete strength. They age also, and they get better over time. But more importantly, because of the grouping of structural members, not every member is designed at the capacity. We group them, many beams and many columns will be above that, because we can't keep changing reinforcement for every. So we take the critical one and we apply in many groups. So the overall capacity of the structure will be much greater than the visual capacity of the members. So that's why this overstrength factor is added. And then we have the total net reduction from the dB to the nonlinear level. And then the R can range from 1.5 to 8. Omega can range from 1.5 to 3.8 or 3.5. So there's a big range in which this red line can follow. We don't know exactly where it is for a structure. This is the code's intent to be here. But the nonlinear procedures that we're going to talk about today can actually find out where this red line is exactly. Theoretically, of course. Now, the ACI strength design level is here at this point, which is just above the yielding or just at the yielding level. And then the detailing rules take us to that level. So they make sure that the deformations will be large and still the structure will not fall and the demand can be reduced. So these two things combined together, strength design for brittle sections, brittle members, and ductility design for members that can, or sections that can be ductile, we combine together and we do this. So you can see here the detailing requirements from ACI. There are so many. There's a new manual and it has so many details. And these detailing requirements often go above and beyond the strength design. So which means that this actual strength is maybe much larger than the capacity that we calculated on which we started, because the detailing rules will further add capacity to that. And in many places where design may not require. So with that, we can see that the structures actually omega could be larger. After we optimize a building a lot, the omega can become smaller, but that has to be evaluated carefully. So if we are going now to the next stage of not doing the code, we are code reliance on R and omega, we can determine the nonlinear response directly from the structure, and then we can compute directly the reduced demand because of the yielding and all, and then we can calculate it for the maximum credible earthquake and also at a service level earthquake, and check the serviceability, check the cracking, check the whether it's damaged or not, and the collapse. So we can check all those performance indicators, performance states at our determined nonlinear response. And that is how the performance-based design is started. So going back to the code, you can group the code into these 11 sections. I don't need to go into a lot of detail, general framework and references, and chapter 1, 2, and 3. Then we have structural system, loads, analysis, 4, 5, 6. Then slab system, 2 chapters on that. Then flexural and axial members, for example, beams, columns, and concrete, plain concrete, those chapters here. And then we have special elements like walls, diaphragms, and foundation, chapters dedicated to that. Then joints and connections and anchorages and so on will be here in these 3 chapters. And then there's a chapter on earthquake resistant design, which talks about most of the things that I presented earlier on top of the other provisions. And then we have material requirements and durability. Then comes the design strength and detailing, which is actually basis for all the components. Normally, it used to be earlier, previously in the earlier course, design and strength and detailing used to be before the discussion of members, but now it is moved up on the course, almost towards the end. And then we have the construction and the most importantly, evaluation of the existing buildings a little bit. And then most important now is the one that for this webinar is the group 11, nonlinear and advanced methods, which is chapter appendix 8. This is for design verification. So to do that, we need to model the structure in detail. And Dr. Pramin is going to, I'm sure, going to go into a lot of detail, how to create hinges, how to create moment curvature, how to create moment rotation, how to assign between the hinges and various types of hinges, and then do the nonlinear analysis, and also do the dynamic analysis to determine the demand, dynamic nonlinear analysis to determine the demand, and calculate the performance indicators. And finally, the performance evaluation. So all of this is intended to answer the question, and the appendix A will help to do the left part. Right part is normally done by ASC and other guidelines. And this is where this chapter, if you look at the appendix A, you will see that they are actually referring to the start of the chapter. They refer to these guidelines, which are on the right-hand side, ASC, TPI, and LATBC. Now, ASC has always been in the code, but the TPI and LATBC, these are new. So this is a basic reference, which is in the body of the code. But this one, the alternative methods from the Tall Building Initiative and also from the Los Angeles Tall Building Structural Design Committee these are the rules that were developed for tall building design long time ago, almost 20, 25 years ago. And in AIT and AIT Solutions and CSI Bangkok, we have been using these guidelines for a number of years for evaluation of and design of many tall buildings. But now they are coming as a reference to the ACI's body through this appendix. So that means these references previously, which were isolated, are now referred by the code, but as an appendix. So anybody who wants to use those, they can use the reference from the appendix and use those guidelines. And most of these discussion will come from there, and Dr. Pramin will explain that. So basically, ACI Code Appendix A graduates to the next level of performance-based design from code-based design and moving upwards. And you can see last time I showed this slide that engineers normally hide behind the code portion, but when we do the PPT, then they can answer most of the question because they have actually done a real evaluation in full detail. ACI 318 Appendix A is still not full PPT. It's just nonlinear modeling part and some provisions from PPT, not completely. So this portion, ACI Appendix A, of answers some of those questions, but most importantly, it addresses design verification. That means it gives you a tool to verify the design that you carried based on the code. So your responsibility is not only to follow the code now, you also have the ability to verify that whether your design for this particular building will work or not. So this is the progression of design. ACI 2019 Appendix A brought seismic design to performance-based level. And the new code, which is released just in this year, in January, February, not released to public yet, is the ACI 25. And it has added a new appendix, Appendix B, which is dealing with PBD for wind, which is a very new method. It's still in development, but the code is already adding it into this appendix, another appendix. And it has another appendix, Appendix C, which has started to talk about resilience-based design and sustainable design. So as you can see here, that the codes are rapidly catching up on the design progression. 10 years ago, when I used to present this hierarchy, the codes were very far behind. The Appendix A wasn't there, and everything wasn't there. So now that we have codes catching up, very soon the code's main body will start doing this thing, and these appendix will move to the main body as they've done always. So we should start preparing to understand these provisions, and that's why we are conducting this webinar today. So next, Dr. Pramin will talk about the details on the guidelines, basically to verify the design. And the intent is that not only we follow the spirit of the code, but we also verify the spirit of the code. And that's the very brief introduction to what Dr. Pramin will present, because to me, that is the major part of the webinar today. So with that, I will thank you all. Please also look at the previous webinar videos that we conducted last week, where we go into more details of PVD and how to use ETABS for PVD. So thank you so much, Samad. So back to you.
Thank you very much, Dr. Naveed, for such a detailed presentation.